Hello everyone. In this video, I will have a short overview of what I said in my presentation in FreeFEM Days 11th edition. Indeed, I tried to record my voice during my presentation there, but I made a bad mistake. I put my recorder in my pocket and the sound quality, the recorded quality was super horrible. So I decided to record it again, but this time shorter, just as an overview on the main concepts behind of my presentation there. Indeed, in that presentation, I demonstrated how I used FreeFEM in order to model biodegradation process as an example of systems, the reaction diffusion systems with moving boundaries. In the beginning, I discussed about the way that our team has used FreeFEM through a couple of years. For about 6 years, we've been using it for computational tissue engineering applications, for degradation process simulations, and also tissue growth. And of course, bioreactor systems involved fluid flow and this sort of things. At the beginning, diffusion reaction systems are systems that are somehow involved with reactions, the concentrations or the state variables that are changed through some interactions, and as well as diffusion, transformation, transmitting of objects or components or species. And moving boundary problems that are usually referred to as Stefan problems are the systems in which you have to define the interface or the boundaries as part of the solution of the system, of the equations. And when it comes to diffusion control interfaces, we can say that the diffusion or reaction systems lead to the change of the domain geometries, and these are reaction diffusion systems with moving boundaries in general. And degradations process, corrosion, for example, is an example of such a system. And the main goal of this presentation and this project is how we model such a system from a mathematical, chemical, and computational perspective. The biodegradation system is a continuous and repetition of sequence of processes that firstly involves the solution of the bulk material in the middle and the formation of a protective film on the surface which protects the material underneath. An example of that would be the rust surface on the iron when it corrodes. And the effects of ions in the medium, in this example for tissue engineering applications, the effects of ions or chemical components surrounding chemical components. So the protective film would be eroded, would be eliminated, and we have an increase in the degradation rates. And in this regard, the moving boundary, as also shown here, is indeed the interface between the material, between the metal bulk and the surrounding medium that moves due to material loss. An example of this would be when you put some material inside your body, you don't want them to stay there forever. For example, in hip joint replacement implants, you want a part of the implant be from biodegradable material. So when the tissue, in this example, the bone, grows, you want the implant be replaced by the newly formed bone, and you need to tune the degradation parameters to the rate of the bone growth so you won't have implant failure. And this would be an example of such a model in its final form in biomedical engineering field. Before going to construct a mathematical model, we need to know the chemistry by degradation, and here's some chemical reactions that are occurring there. And I'll discuss this in other presentations, but here we have the elimination. Indeed, the oxidation of the material, the reduction of water, and formation of a protective film, which is here magnesium hydroxide, and also elimination of that film due to the presence of some ions here, chloride ion as an example. In order to construct a mathematical model out of the chemical model, we define two state variables here, the concentration of magnesium, concentration of film in the 3D space, and we define two reaction diffusion equations, PDEs, for these two state variables that contains diffusion terms for the magnesium, also reactions for both PDEs, and we define the saturation terms for penalization of the magnesium concentration as an effect of the presence of the film. It's also worth noting that the diffusion rate here is not constant. It's not a constant variable. It's also a function of space and time because it's a function of the concentration of the film. In order to track the interface, we take advantage of defining an implicit sign distance function through a level set method. And the level set method takes care of tracking of this function, and the zero isocontour of this function, which is here phi. This is function of space and time in 3D space. This zero isocontour of this function is the interface. So if we solve this PDE, this level set PDE for each time step, plotting the zero or the roots of this function or the interface. So by just tracking that, we can say that where is an interface at any given time. And inside the material, inside the bulk, metal bulk, it is positive, the function is positive, and outside it is negative. So by calculating where it's positive through the space, by integrating through the space, as I always show you in the upcoming slides, we can say we can calculate the material loss somehow. What is important in the level set is computing the velocity. Here we assume that the velocity or the degradation direction is normal to the interface, so the level set equation will be simplified to this one, and then we take advantage of known equations to correlate flux of the interface, flux of the mass on the interface to the velocity of the interface, known as Rankine-Haganen equations. And then by having a closer look at the interface, we can just substitute the values into the equations and then write the final form of the level set to be solved. So this is the final form of the level set equation that we have to solve alongside with the previous two PDEs. The challenging part of this is the computed normal gradients. In order to construct the computational models, we take advantage of finite element model, finite element analysis, and finite element method. In order to do that, we need to have the Wick formulation of the equations. We define two trial and test function space with non-flux boundary condition on the borders of the domain. If we write the equations and multiply by those by any arbitrary function v, and integrate through the whole domain, and then using integration by part techniques and Green's divergence theory and the backward Euler scheme for as finite difference scheme for the temporal term, we can have this equation, which can be rewritten to a command form of Wick formulation for diffusion reaction systems by defining a linear functional and multiplying to a new coefficient alpha. So this is the final form of the Wick formulation. The next step is implementing this, and this is where FreeFEM can help us in order to facilitate this process. And we define a new function space, basis functions, which are here first order Lagrange polynomials. The current state variables is considered as a sum of coefficients multiplied by basis functions at each node, and also the previous time steps with known coefficients. So the Wick form can be now written into the sum instead of integration form. which is indeed a linear system of equations with the A and B is defined here. And such final form, such a form can be implemented in FreeFEM easily. This is what we've done, and we have also employed parallelization techniques in order to make it to run faster. But before going to parallelization, there are some issues involved in levels of implementation. We use penalization for the interface boundary conditions. So on the interface, we have penalized magnesium concentration and also the film coefficients on the interface. But doing this will impose some difficulties in computing normal gradients and also the diffusion coefficients. In order to overcome this, we use lumping, which can prevent lumping feature, mass lumping of FreeFEM, which can prevent some oscillations, but at the same time, we've still some problem to compute the gradients on the interface, which is a very common form of problem when we are working with interfaces. To overcome this problem, this issue, we compute the gradients on a distance h from the interface as shown in the figure. And h is the size of the smallest element in our computational mesh. But doing this, we can overcome the issue of too big or too small gradients. But at the same time, it requires redistancing of the distance function, because when you advect the distance function, it will be distorted. So you need to redistance it. But the problem, the scheme that is employed in FreeFEM to implement the redistancing of the phi function, of our sine distance function, has some problem. So we have some artificial movement of the interface, and we have to deal with that as well to correct it or to ignore it completely, or mixture of these two techniques. So there's already problems of the levels of implementation indeed. The computational mesh is an Eulerian mesh in which we put both domains, medium and the implant or the metal bulk indeed inside. And we refine the mesh on the interface based on the phi function, and it helps us to have better accuracy on the interface due to problems with level set and oscillation. And the mesh is generated using NetGen and Solon platform. In order to parallelize the code, we took advantage of message passing interface, MPI, and we have developed distributed numerical integration in which we assign a number in the range of 0 to the MPI size -1 to each element, uniformly or non-uniformly, but equally. So each MPI core, each MPI node will have a certain number of elements to perform the numerical integration on. And then we assemble the matrices and use MUM's multifrontal direct solver to compute the final solution in each time step. Here is a quick glance of the numerical simulations that shows that the level set equation is working fine, and also we have the diffusion phenomenon here that works homogeneously as expected, and we have the degradation of the simple screw that you see here. And these white surfaces are indeed the post-processed results of the phi function. We ask our post-processor, ProView in this example, to plot the zero isocontour of the phi function. And as a result, we can see how the material is degrading over time just by the output of the level set equations, and all the surrounding concentrations are the results of that diffusion reaction PDEs. And this is a formation of the predictive surface that was for the second PDE, as I showed you, and which have some effects on the degradation process and rate due to that saturation term, penalization term indeed. This is another example for per structure that shows how a protective film is formed on a surface and how the material degrades. To have quantitative results, we can use the level set output, level set model output for calculating the difference between the volume that are available at each time step. This is the dimensions of the sample setup that we had in order to compare the quantitative data predicted by the model and obtained from experimental tests. And here is the result that shows how the side product is evolved, which is a way indeed to assess and monitor the degradation instead of a direct mass loss measurement. And on the left, the formation of the film can be observed. On the right, the comparison between the experimental data and computational data which are predicted by the model. And we've also performed some performance analysis tests on the data. The problem size, the setup is the same as I showed you for the numerical setup validation. The degrees of freedom is around 150,000, and the elements 800,000 with the degrees of with the precision of first order. And the meshes adaptive refine an interface. The first is the domain decomposition. We had two different approaches for distributing nodes through MPR cores. One is uniform, and the other is non-uniform. And here the results demonstrate that there is no significant difference between these two approaches, so it's safe to randomly distribute the nodes through MPR cores, which is much easier for higher number of MPR nodes available. And we had weak scaling tests in which you double the size of the problem while doubling the available computational resources. So ideally, when you double the size and double the computational resources, you should have the same runtime. Here, the runtime for each time step is plotted cumulatively, and when it's broken down into contributions, it can be seen that as we double the size of the problem and the available MPR nodes as the computational resources, we have still an increase in the runtime, which means that the parallelization approach is not very efficient, at least from a weak scaling perspective. And in these scenarios, usually Gustafson laws is used to compute the serial proportion of the code when we plot MPI size and speed up, and we fit the same equations on the obtained data. In this example, the serial proportion is 86%, and only 14% of the code can be parallelized, which is not a very good result in this matter. But we also perform a strong scaling test in which you keep the problem size constant and increase the computational resources, in this example available MPR nodes. And we can see that by increasing the available MPR nodes, we have a decrement in the runtime, but it's not very efficient. As can be seen here, the parallel efficiency is very low, but we do the same principle as we did in strong scaling by using a new rule MD handlers, which is a common way of analyzing strong scaling test results. And then by plotting this, by fitting that equations on the obtained results, we will have a serial proportion of 52% and parallelizable proportions of 48, indeed half, so half of the code can be parallelized from the strong scaling perspective. In this presentation, so we talked about how to construct a quantitative mathematical model and its corresponding computational model based on finite elements for the assessment of the degradation process as an example of diffusion reaction systems with moving boundaries. And we showed how we used element level set method to track the moving corrosion front And in the final form of the model, when it was fully validated, it can be used as an important tool to find the right design properties of biodegradable materials.